Welcome to the second part of the complex regressors lecture. I'll be starting on overhead 42 about polynomial regression. The title of this chapter is Complex Regressors and More Complicated Structure. And so here's our first introduction to a more complicated way and sophisticated way to handle quantitative regressors. If your data is suggesting a mean function that is smooth, but it's not a straight linear function, you can approximate smooth curves frequently by some kind of a polynomial. Here's a really easy example one, a degree 2 polynomial called a quadratic that would have just one bend or curve in it, and you can build a mean function that has the predictor variable regressor x to the first power and add a sort of new variable, the same regressor raised to the second power, and this enables you to model a curve. And this kind of parabolic curve will achieve a maximum or a minimum, and this is the place on the x-axis where you'll have a peak. It involves the beta 1 parameter and the beta 2 parameter to determine where that peak will occur. This is called polynomial regression. There's no reason why we can only have to use a degree 2 polynomial. We might be able to use a degree D polynomial with increasing powers of the predictor variable x. Degree 3 is called a cubic. Degree 4 is called a quartic, degree 5 is a quintic, and if you have very complicated functions, you might need higher powers of the polynomial to match the curving. Pretty much anything beyond degree 3 is quite rare. A degree 3 polynomial will be able to accomplish a curve that will bend and have two bends in it, and that's usually what we need to be able to do. Here's an example to illustrate it. I'm making some fake curved data here, and I'm using a model M1 to try to explain the relationship between y and x. There's a single x variable, but I'm going to model y in the mean function with the variable x plus the identity function of x squared and the identity function x cubed. The reason I need to wrap these x squared and x cubes in the identity function is so that R understands that those are functions and not variables. It'll be confused and look for a variable called x hat squared, and it won't be able to find it. In the identity function, it realizes I want to use the x squared function. And notice that after you've estimated such a model, you get a term, the beta hat 1 multiplying the x of 4.89. You get a beta hat 2 multiplying the x squared term, negative 2.97, and a beta hat 3 of negative 1.05. Another way to do a polynomial is to use the poly function. And so I've done that here, model M2, linear model of y as a function of a polynomial of x, degree 3, so we'll go up to third power. Raw equals true just means use the basic polynomials. And you can see what you get. You get the same beta hat estimates as you did using the identity function. The benefit from using the poly function in R is that you can use the effects plot. And so here is what the effect plot looks like relating the data y to the predictor x. And you can see the curved pattern that's being represented by this cubic polynomial. If you use the identity function, you'd get a separate effects plot for x and x squared and x cubed, and that's really hard to interpret. This is really a one variable to one variable relationship, and so the poly function lets you get an effective effect plot that you can understand. There's no reason why you can't use polynomials on more than one regressor or predictor variable. Here's a case where I have two quantitative predictor variables, x1 and x2, and I've got x1 raised to the second power, I've got x2 raised to the second power, and I've got a multiplication of x1 and x2 in kind of an interaction here. And this would be able to represent a curved surface, possibly. And we might need a mean function that is complicated like this. I'm not going to talk too much about the delta method here on the video, but it's a way to estimate estimates and standard errors for estimates complicated functions of these beta parameters. Here's an example of a polynomial mean function. We've got an industrial experiment making cakes. Our response variable y is the taste score of how good the cake is and how pleasing it is. The first factor is the baking time. It's a quantitative variable in minutes. And x2 is a quantitative variable in temperature. And so we've got temperature in degrees Fahrenheit, it looks like, and x1 is in baking time in minutes. And here's a model that we talked about before. We have baking time, baking temperature, time squared, temperature squared, and the multiplication of time and temperature. And here are the model coefficients, and you can see that from all of them, they all have very small p-values, suggesting that each of these affects this sort of curved pattern with time is important. And there's a curved pattern with temperature that's important. And notice that for these squared terms, they are negative values. And if you remember back to your high school algebra or pre-calculus class, when polynomials have negative values for the squared terms, it's a concave down kind of relationship like you're seeing in this display. And so the taste is achieving a peak for any fixed amount of time or temperature. Here in this display we've got temperature, we have time on the horizontal axis, the various times that the cake is cooked, and the different profiles are the different cooking temperatures. And you can see that from this display it looks like the maximum taste is happening at about 36 minutes of cooking at a temperature of 350. And that's achieving the highest taste score. And that's why we might need to use a complicated function to determine where this maximum occurs, and you might need calculus and the delta method for coming up with what is the value where the maximum occurs and what's the standard error. Here's the effect plot for that model, and we have the x1, the cooking time, on the horizontal axis, and the different panels are the different values of x2, the temperature. And so the way you would read this, x2, you can see the little dark orange bar over here. These are the lowest cooking temperatures here, and you can see that the cake tasting increases with cooking time. Basically, if you don't, at this low of a cooking temperature, you need to cook it longer for the cake to be good. And then we go up to the next level of cooking temperatures, and then we go up to some more cooking temperatures in about the middle of the scale, and then we go up to the next level, and finally the highest cooking temperatures. And you can see that there's kind of a curved relationship between cooking time and taste, no matter what temperature you're at. But you can see that the highest taste tends to occur at about 36 minutes of cooking time, and at about, not clear what the level of x2 is there, but at about this level of x2. And that's another way to sort of understand the surface that you're estimating. Another way to handle curved relationships is through a technique and method called splines. Instead of having polynomials or a weighted sum of these x to a power functions, what you can do is have different functions other than x to a power. Have a function b1 of x up to bd of x. Sort of different basis functions rather than x to a power, have different kinds of functions. And those kinds of functions are called splines. Basically, these little functions are going to be little cubic functions defined at different places along the x-axis. And so you can estimate a mean function or display a mean function with a weighted sum of these new basis spline functions. And the beta coefficients are going to be measuring how much weight to give to each of these basis functions. Usually we've been able to interpret these beta coefficients, but with a spline model, these are just weights and they're really not interpretable. You're going to need effect plots and graphical displays to understand the spline relationship. In general, the more basis functions you use, the more complicated patterns can be summarized. Fewer basis functions will enable you to explain less complicated curved patterns. If the curved pattern is quite extreme and has lots of bends or very extreme bends, maybe you'll need more basis functions, higher value of d. If it's a more gradual curved pattern, then smaller numbers will be enough. And it's really kind of an art to figure out what the right number is, and you just learn that through experience. Here is an example using the body weight and sleep time as the response from our animal sleeping study before. We're going to just explain time slept with the log of body weight. Remember, we were using straight lines before, but maybe this relationship between log body weight and time slept is a little bit curved. Let's use a spline approach to summarize this. We're going to use degrees of freedom equals 3. That means little d. We're going to use 3 basis functions. Each of the basis functions are going to be little cubic polynomials, and we're going to specify a spline model. We're going to need the splines package to run this, and here is the effect plot for body weight as a function trying to explain time slept. You can see we get a downward pattern like we were seeing before. There's a little bit of curve in here. It's almost linear. The splines were not terribly needed here because it was almost a gradually line pattern, but there's a little bit of curve here. So there's some mild nonlinearity, and we really don't need a number of basis functions that's more than 3. This is more than enough. If you had a very complicated relationship, maybe you'd need more than 3. Here's that x and y data that I used previously to describe and estimate a polynomial. Here is the raw y against x data. You can see the pretty big curve here. And if I want to use a spline, it's the BS function for the predictor variable, 3 basis functions and cubics for each of them. And here is the effect plot, and you can see it's pretty similar to the polynomial that we saw previously. Referring back to the polynomial that we estimated and displayed back here on overhead 46 for the polynomial. And that's for the splines. Another thing that can happen in real data is we have collinearity, or we have lots of predictors that are all basically measuring the same thing. Here's a data example from ratemyprofessor.com, and we have 5 variables that students have evaluated their professors: overall quality, helpfulness, clarity, easiness, and how interesting the person was in the course or in the instructor. And you can see that a lot of these variables, like helpfulness and quality, are almost perfectly correlated. And clarity and helpfulness are very correlated. And clarity and quality are very correlated. And even some of the rater interest and quality are correlated. So there's 5 variables here, but there's a lot of overlap between these things, and the 5 variables probably really are not totally needed. They don't map out a 5-dimensional space. Maybe we could summarize the information in these variables with a smaller number of variables intelligently constructed. So could we summarize these 5 variables, the information in them, with maybe 1 or 2 or 3 variables to simplify our situation? Remember, the trouble we get into sometimes in regression models when the regressors are all very correlated. We get a difficult time with interpretation and signs and coefficients changing a lot. So if we could address that issue, we might be able to make an analysis more informative and more reliable. And we do that through a technique called principal components analysis. So here's the situation. We have a large predictor set with k predictors, and k is a big number, and we'll represent that predictor set with the matrix X transpose with all those predictors in there. And the issue is, can we replace a k variable set with a smaller set with k naught less than k? Can we make linear combinations out of the original variables, sort of new variables out of the old ones, that basically summarize the situation sufficiently that we don't need to use the whole variable set, we use a subset? So the way we proceed is to make a single variable out of the original set. And the single variable is called Z1, and it's a combination of the original variables. And we make the variable Z1 with a combination of original variables so that Z1 has the biggest variance as possible. And it turns out that is like the single best variable that can be made out of the original set. You want to capture the essence of the original set, or in other words, what is the variable or the direction that has the most variation in the original set? Well, let's make a matching one out of the original set, and that's Z1. It turns out that that linear combination of the original variables is defined by this little coefficient vector U1, and U1 is the first eigenvector of the variance matrix of the variable set. You'd learn this in a linear algebra class. The variation of that first variable, Z1, the biggest variation you can get, that variance is called the first eigenvalue, and we have notation for that, lambda hat 1. That's the single best variable you can make out of the original set. The second best variable is to make a variable Z2 so that you have the most variation that you can make in a direction that's perpendicular to the first variable. And it turns out that that second variable is the second eigenvector, and the variation of that second variable is the second eigenvalue. In principal components, you can talk about the overall variation of the original set as the sum of the k eigenvalues when you do principal components on the original set of variables. And the idea is that if the first couple of eigenvalues are almost the same size as the sum of all of them, maybe like 80–90% of the entire sum, then maybe the first two variables are a good approximation for the entire set. And then in such a case, you would represent the entire collection X with only two variables, Z1 and Z2. And that's the case what we have here in the Rate My Professor data. We take the 5 variables, we perform principal components analysis using the PR-comp function, and we get a principal components object called Z, and we summarize it right here. The first eigenvalue is 1.57. It's 78% of the total variation. The first two variables, the first eigenvalue is this one, the second eigenvalue is 0.622, and between the first two variables you explain about 91% of the variation in the entire collection set. If we go up to 3 variables, you explain about 98.1% of the variation. So we can basically summarize 5 variables with 3 new derived ones. The first 3 eigenvectors. Maybe the first 3, maybe the first 2, they're both very good summarizations of the entire collection of 5. Well, that tells us how many variables we can summarize the entire collection with, either 2 or 3. Even 1 variable is summarizing about 80% of the variation. What are these new variables? Well, we need to look at the components of the principal component object, and under PC1 we see the U vector. This is basically U1. Under PC2 we get U2, and under PC3 we get the U3 vector, which defines the new variables. If we go ahead and take a look at U1, we can see that the multipliers for the quality, helpfulness, clarity, easiness, and rate or interest, what you're supposed to observe is that the first 3 components are all about the same size. It doesn't matter that they're negative, but they're about the same size, and they're treating quality and helpfulness and clarity in a kind of combination summary variable. Easiness and rate or interest are not being used. These are lower weights, and they're down weighting and really not using the easiness and rate or interest. The first variable, Z1, is really a combination of quality, helpfulness, and clarity. The second variable is really driven by just easiness. This weight is very high for easiness and really low on all the other components. The second variable, Z2, is an easiness variable. The third variable, Z3, is really in how interested is the user variable. And these would be the 3 variables we would use in a new model. These first 3 variables would be the ones we would use instead of the entire collection of 5. To sort of see this in action, I'll put in the first Z1 variable into the scatterplot matrix so you can see what happens. That's this predict Z1. That's the first principal component variable. And you'll notice it is almost a perfect surrogate for quality, helpfulness, and clarity. It's not nearly as related to easiness or rate or interest. So this new variable, Z1, would be used in the place of clarity, helpfulness, and quality, and we would simplify 3 variables to 1. Here's the second variable, Z2, plotted against the others, and you can see that that second variable is very correlated with easiness, because after all, that's what's making it. And you'll see that this second principal component variable is not related at all to the helpfulness and quality and clarity. And that'll improve our model a lot. And so we would go ahead and make a model that would use the Z variables instead of the original X variables. And we'd have much better performance and more interpretation. Everything up till now is assumed that we've had complete data and no missing observations, but values are often missing. Our software assumes that we have complete data, and so what do we do if we don't have that? What are we going to do about analyzing data when there's pieces that are missing? One thing you can do is you can delete all the observations that have any missing data. And that's fine if the data are really missing as a random process. But a lot of times the data and observations are missing probably because of the attributes of the variables might contribute to their missingness. And so if they're missing and we just throw things away in an arbitrary fashion, we might get misleading inference. There is a nice command in R that will force you to use complete cases, and so you can come up with a complete no missing data set using the complete cases command on a data frame. And so in a model you could do data equals complete cases data frame, and you would have a data set with no missing values at all. However, sometimes putting in fake data called imputation or good guesses for the missing parts is better than doing nothing or ignoring the problem. And some packages for doing imputation are mice, Amelia 2, MI tools, multiple imputation tools are packages in R that help you do that. And basically the strategy is when you do imputation or multiple imputation, what you do is you make like 5 duplicate data sets, all with different randomly, intelligently placed guesses for the missing values. And the final results are an average of the analyses of your 5 artificially created data sets. This is a real active research area, and so please always consult online for the current advice about how to do this. Here's an example using some functions from the mice library on one of our data sets in our book, Minnesota Land. And the purpose of this is to show you how to find out about missing data in your data set. And on overhead 69, you'll see how to read this output. So we'll do missing data pattern function on the Minnesota Land data frame. And the first row says that there's 8,770 cases that have absolutely complete data on price, region, year, acres, financing, crop percentage, improvements, tillable, and productivity. The 0 here in the last column means no missing variables at all. So there's 8,770 rows in the data frame that have no missing data. There are 17 rows in the data frame, this next row, where what variable? Improvements have missing values. So there's one variable with missing data, it's improvements. There's 17 cases where that's the case. There's 196 rows in the data frame where the tillable variable has missing observations. There's 8,671 rows in the data frame where the response productivity is missing. And then the rest of these show combinations of 1,013 observations where both tillable and productivity are missing. And there's 3 observations where improvements, tillable, and productivity are missing. And so it gives you an idea about what variables have missingness, and it might give you some guidance about what to do about it. And that's the summary in overhead 69. Let me know if you have questions.